Hi, in this lesson, we're going to learn about the electromagnetic spectrum. We'll learn the different parts of a wave. We'll learn how electromagnetic radiation is comprised of an electric field and a magnetic field varying, and we'll see how that electric field can interact with atoms to promote electrons from one energy level to another. We'll also learn how to calculate the energy and wavelength and frequency of electromagnetic radiation using two general equations, two relationships. All right, so electromagnetic radiation, this is also known as light, but in fact, it encompasses everything from radio waves all the way to gamma waves or gamma rays. So an electromagnetic wave consists of a varying electric field and at right angles to that, a magnetic field, which I'll illustrate this way. Okay, so the electric field is in this plane, and in a plane at right angles is the magnetic field. And this is varying in time. So we can think of this as a wave that's moving in space, or we can think of it as moving. If we look at one space, it's moving in time. So the wave is going up and down, or we can think of it as moving through space. Okay, so we've got an electric field and a magnetic field, usually B to illustrate that. And because electric fields interact with charged particles, the electric field is going to affect the electrons in atoms. And there's a range of energies that these waves can carry, and that energy is proportional, this little fish means proportional to the frequency of the wave. In other words, how many waves pass a point in a given amount of time, say so many waves per second. And it's inversely proportional to the wavelength. So we have the expression energy is equal to h nu, and that's equal to hc over lambda, where nu is the number of waves per second, or the frequency. That's a Greek letter nu. Lambda, that's a Greek letter, I'll write the name. This is a letter N. It's a Greek N. This is a Greek L. That's equal to the wavelength. So L for length, N for number. And H and C are constants. H is called Planck's constant, and that's, you don't have to memorize the value, but it's about 6.626 times 10 to the negative 34th joules times seconds. So that's an energy relationship. And C is the speed of light, which is the same for every different wavelength, from radio waves all the way to gamma. And that's equal to about 300 million meters per second. Okay, so you can use this expression to calculate the energy carried by a wave or by one photon of any particular wavelength or frequency. We can also relate then the frequency and wavelength. We can say that frequency is equal to the speed of light divided by the wavelength, or maybe easier to see, wavelength times frequency equals the speed of light. Length times frequency equals the speed of light. And length is in meters, and frequency is in number of waves per second. So it's in reciprocal seconds, and so you end up with meters per second. Okay, so that's our relationship. Now let's look at the bands of the electromagnetic spectrum. And you've learned this before, but here we go. Radio, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And for these, wavelength decreases as we go from left to right. Frequency increases because they're inversely proportional to each other, and energy increases as we go from left to right. Radio waves, these are of the order of meters long. These are kind of centimeters. These are maybe micrometers. Visible light is hundreds of nanometers. UV is smaller than 300 nanometers, roughly. And then X-ray, we're getting down into maybe tens of nanometers. And then gamma rays are going to be anything smaller than X-rays. All right. So I think it's important to have an idea, certainly to know the order of energy, to know that ultraviolet is a higher energy than visible light. And this radiation here, this is called ionizing radiation. And the reason for that is that there is enough energy in these photons to knock an electron clear out of it. Now let's relate electromagnetic energy to the atomic structure that we talked about in the last video. So here's an atom, put a little nucleus here, and we'll put some electron shells around it. And remember that the shells get closer together as we go out. I didn't mention that in the last video, but you probably remember that. So when light comes in, if there's an electron, say, in this very first shell, if a photon comes in, if it doesn't have enough energy to knock the electron all the way up to the next shell or to the one after that, if it's only got enough to go here, that electron is not going to move. There's not enough energy to promote the electron to a higher level. If the photon coming in has enough energy to get you up here, then we promote the electron up to a higher energy level. If it's got a little more energy, maybe it can go up to this energy level here, okay? The electrons that can promote an electron out of the first shell, well, in a hydrogen atom specifically, those would be ultraviolet. To go from the second shell, so this is first shell, to any other shell. Visible light will start with an electron in the second shell, and infrared is going to start in the third shell. Why? Because the shells get closer and closer together. If I redraw this as an energy level diagram, if I put the first shell here, the second shell here, third shell here, a little closer, see how they're getting closer and closer together. An ultraviolet wave will have enough energy to get from here up to a higher shell. Visible light can't do that. Visible light will let us start here in the second shell and get up to another shell. And infrared will let us start in the third shell and get up to a higher shell. And there are names for transitions from the first to another shell or from second. They're called the Lyman series, the Balmer series, and the Paschen series, but I don't think you need to know that. But I'll write it just for if you want to look it up. Lyman, Balmer, Paschen. So these are energies that can be absorbed by atoms as light shines on them. Okay. The UV light or X-ray or gamma has enough energy to knock an electron, not just to a higher level, but actually all the way out, and that's ionization. And that kind of change isn't so good for our bodies because an atom who's lost an electron is going to be looking to get an electron from somewhere else, and that makes it very chemically reactive, and that can lead to a problem with our DNA by chemical reaction. If a water molecule, which our body has most of, gets ionized, it's going to grab an electron from somewhere, and if it grabs it from DNA, then that DNA is going to undergo reactions and possibly mutations or other changes. Okay, let's see. One final thing, I guess, we'll go ahead and wavelength times frequency equals the speed of light, and Planck's constant times frequency equals the speed of equals the energy, or if we combine those two equations, then it's Planck's constant times the speed of light divided by the wavelength. So let's do a calculation. Let's calculate lambda given frequency equals 2.5 times 10 to the 14th hertz, or 2.5 times 10 to the 14th per second, waves per second, right? That is seconds to the -1 or 1 over seconds. All of these different units mean the same thing. So how can we calculate that? Well, lambda is equal to speed of light divided by the frequency. That's equal to 3.00 times 10 to the 8th meters per second. Please always write your units. Divided by 2.5 times 10 to the 14th per second, or hertz or whatever. This per second cancels that per second. Or if you want to think about it, we're dividing by a fraction, 1 over seconds. That's the same as multiplying by seconds over 1. The seconds cancels. And what do we get for the answer? I don't know. You can put it in your calculator, but it's 3 times 10 to the 8th over 2.5 times 10 to the 14th. It's going to be something like 10 to the -6th meters. Okay, a little bit more than that. Okay, and let's find out what the energy is for the same wavelength. Energy equals, let's go ahead and say hc over lambda, since we know lambda. That's 6.626 times 10 to the -34th. Again, you don't need to know that. Joules times seconds times 3.00 times 10 to the 8th meters per second. The per second cancels with the seconds there. Now we have joules times meters. and we'll divide by 2. What is it? We're calculating. So I should have used the other equation. We'll divide by, we would divide by whatever this answer was here. Let's do the other form. Since we're given frequency, 6.626 times 10 to the negative 34th joules times seconds. And we've got 2.5 times 10 to the 14th per second. Per second cancels that second, and we're going to end up with a number in joules. And I'll pull up my calculator real quick and do this calculation. 6.626 times 10 to the negative 34th times 2.5 times 10 to the 14th is 1.66 times 10 to the negative 19 joules. Okay, that's it for this video. Do a calculation of wavelength and a calculation of frequency. So let's try that. Remember our two equations.